So up to this point, we've looked at how ionic bonds form, why ionic bonds form, and then how we can use Lewis dot structures to represent how many electrons that we can transfer during the formation of ionic compound by looking at the valence electrons for our metals and nonmetals and using that to determine how many electrons a metal will lose and a nonmetal will gain. What we haven't looked at are covalent bonds, how covalent bonds form, and how we can also still use Lewis dot diagrams to think about the formation of covalent bonds. We did say covalent bonds are formed between two nonmetals, and we talked about why that happens, because nonmetals have high electron affinities and they also have high ionization energies, meaning it's hard to remove an electron from a nonmetal. They prefer to gain an electron, and so it's easier for two nonmetals to share that electron, forming a covalent bond, as opposed to an ionic bond where there's a transfer of those electrons between a metal and a nonmetal. Remember, those nonmetals, they have high electron affinities and they have high ionization energies, meaning it's going to be hard to remove an electron from those nonmetals. And it's more likely that those two nonmetals, when they react, they would rather share electrons than transfer electrons. That being said, we can still use Lewis dot diagrams to think about how many electrons those nonmetals need to share, because they're going to share enough electrons to still obtain the noble gas configuration. And that's essentially the octet rule, that basically an element's going to form a covalent bond in a way to share enough electrons to obtain a full outer shell, to obtain a noble gas configuration. So an element in a covalent bond will share enough electrons to obtain a full outer shell. Essentially, noble gas configuration. Right, for essentially all the elements that we're going to look at except for hydrogen and boron, for most elements, that is 8 electrons for an octet. Right, the exception, hydrogen will never have more than 2 electrons. And boron as well we'll also see, but hydrogen, number 1, is the most common exception that we'll see. Most of the elements we're going to work with are going to strive, they're going to react in a way to have 8 electrons in their outer shell, or a full octet, following the octet rule. So we can represent this, right? Here's the Lewis structure of hydrogen. Hydrogen has 1 electron. Here's the Lewis structure of another hydrogen. So when those two hydrogens come together, they each have 1 electron. They're going to each share that electron to have a full outer shell. Right now, they both have 2 electrons, which is, right, isoelectronic with helium, the nearest noble gas. We can use the Lewis dot structure to think about that formation of the covalent bond. Each hydrogen bringing 1 electron into the covalent bond. We share those electrons between the hydrogens, forming that covalent bond. We can also represent that by showing each of the individual electrons, as we've shown it here, or we could just simply say, by drawing a straight line between those 2 hydrogens, that means I'm sharing 2 electrons as represented by that line in that covalent bond. But to think about that covalent bond, we can think about each hydrogen coming in, bringing 1 electron to that bond. Neither hydrogen loses that electron, right? They're going to each share that other electron to form 2 electrons in the outer shell. becoming isoelectronic with neon. How about something bigger? How about something like hydrogen and chlorine forming hydrogen chloride? Well, hydrogen still has one valence electron. Chlorine, being a halogen, has 7 valence electrons. So 1, 2, 3, 4, 5, 6, and 7. So how we can represent this? Well, hydrogen bringing its 1 valence electron, chlorine bringing its 7 valence electrons, having 1 vacancy. When the two come together, right, here are the valence electrons from chlorine, the 7 valence electrons from chlorine, and my 1 valence electron from hydrogen. But at the end of the day, that hydrogen chloride bond represents the sharing of those 2 electrons between hydrogen and chlorine. And if we look, hydrogen has 2 electrons in its outer shell. It's isoelectronic with helium. Chlorine has 8 electrons in its outer shell, and it's going to be isoelectronic right now with argon. So both hydrogen and chlorine are going to share enough electrons to obtain a noble gas configuration. So now we can think about how other atoms might form a noble gas configuration. So let's think of, for example, what would the Lewis diagram for water look like? H2O. How would we represent that with the Lewis structure for hydrogen and oxygen? What would that look like? Within this Lewis structure of HCl, we've got 2 different types of electrons represented. We've got a bonding pair of electrons, and we have lone pair electrons. They are different electrons. And so the bonding pair of electrons are shared. They are what are participating in that covalent bond. They are shared between 2 bonding elements in a covalent bond. And that's different than the lone pair electrons. The lone pair electrons, these are also known as non-bonding electrons. These electrons are not shared between the atoms. They are only assigned to one atom. So they belong to chlorine and chlorine alone. And as you'll see, those are pairs of electrons, right? So in this example here, I've got a bonding pair that represent 2 electrons, and I have 3 lone pairs that represent 6 electrons total. So just be careful. You may be asked for electrons, or you may be asked for pairs. If I asked you how many lone pair electrons, we would answer that as I have 3 lone pair of electrons on chlorine for a total of 6 electrons. I can also represent multiple bonds using these Lewis dot structures. So ethylene, for example, is the structure pictured below. In ethylene, I have my carbon-hydrogen single bond where I've got 2 electrons shared between the carbon and the hydrogen, for each of those carbon-hydrogen single bonds. And between the 2 carbons, I have a carbon-carbon double bond. Each of those bonds represents I'm sharing 2 electrons. So I need to share a total of 4 electrons between those 2 carbons. And let's take a look at my octet rule. Right, for the octet rule, I need to have 8 electrons around the central atom, with the exception of hydrogen. Hydrogen only wants 2. So hydrogen has 2. For the carbon, I have 1, 2, 3, 4, 5, 6, 7, 8 for this carbon. And then for this carbon over here, I have 1, 2, 3, 4, 5, 6, 7, 8. So both of those carbons have 8 electrons. They both have a full octet. So they meet the octet rule. In the next class, we're going to spend a lot more time making Lewis structures for molecular compounds, and we'll work through a host of rules that we're going to use to figure out what is the best Lewis structure. But for now, I'm just introducing it that yes, we can have single bonds, yes, we can have double bonds as well. So within these covalent bonds, we are sharing the electrons. That being said, often those electrons are not equally shared between the two atoms, and that's because of differences in electronegativity. I want you to think of electronegativity as basically a tug of war for that electron density, because electronegativity is basically the ability to pull electron density of an atom to pull electron density toward itself. So we still have a covalent bond. We're still sharing the electrons in that covalent bond, but we're not sharing them equally. Often, because we cover these around the same time, students get electronegativity and electron affinity mixed up. They are different, right? This electronegativity is different. This is different than electron affinity, right? That is the energy released when an atom gains an electron. We're talking about electronegativity, the ability of an atom to pull electron density towards itself. So a tug of war between two atoms, one atom is stronger than the other. So in general, electronegativity increases from the lower left to the upper right-hand corner of the periodic table, where cesium is the least electronegative at 0.7 and fluorine is the most electronegative at 4. So here's the trend in electronegativity, right? It increases from the lower left-hand corner to the upper right-hand corner, where fluorine is the most electronegative element on the periodic table. And the other general trend is that it increases from bottom to top on a group as well. So electronegativity, the ability of an atom to pull electron density toward itself. So what does this mean for my covalent bonds? So here are two examples. I've got fluorine, I've got diatomic fluorine where fluorine is bonded with itself, and I have hydrogen fluoride where hydrogen and fluorine are bonded together. I can draw the Lewis structure for both of those, right? Here's the Lewis structure for diatomic fluorine, and here's the Lewis structure for HF. So what's important here is the color of these structures. Fluorine, F2, diatomic fluorine, yes, fluorine is very electronegative, but when you bond fluorine with itself, in this case, right, you've got a pretty evenly matched tug of war. You're going to have a tie for those electrons. So that's what you see in the green color represented in this image. It means you have an equal distribution of electron density, right? You don't have a surplus of electrons on one side because you've bonded the identical elements together. You've bonded fluorine with fluorine. So yes, it's electronegative, but because we're bonding it with itself, we have a tie for that tug of war for electron density. That's much different in the hydrogen fluoride, where fluorine is much more electronegative than the hydrogen. So as a result, I'm going to have much more electron density on the fluorine. And we see that in this image. So the red color of this diagram indicates a much larger electron density on this side of the molecule. I'm going to have a larger electron density on that side because fluorine is more electronegative. It's going to be able to pull the 2 electrons in this covalent bond. Instead of being equally shared between the hydrogen and the fluorine, right, those 2 electrons are going to be closer to the fluorine because fluorine is more electronegative. And that's what we see in this density. I'm going to have a larger partial positive on the hydrogen side because I'm pulling those electrons closer to fluorine. And that's what it's indicated with this vector here, just indicating that fluorine is pulling the electron density closer to itself, farther away from hydrogen. So these differences in electronegativity set up a couple different bond types within covalent bonds. And so we're going to have polar covalent bonds and nonpolar covalent bonds. Nonpolar covalent bonds, we're going to essentially have equal or almost equal sharing of electron density. Distribution of electron density in a covalent bond. Examples of nonpolar covalent bonds, like we already saw with diatomic fluorine, right? 2 identical atoms bonded together, my electronegativity is identical, it's going to be a tie, right? I'm not going to have an unequal distribution of electron densities. So diatomic fluorine or diatomic nitrogen or oxygen or hydrogen, all of those would be nonpolar. I'm going to get an equal sharing of electron density. Other examples, common examples, would be something like a carbon-hydrogen bond. Carbon and hydrogen have a very similar electronegativity, and I'm going to have approximately an equal distribution of electrons between the carbon and the hydrogen for a nonpolar bond. On the other end of the spectrum, and that's like the HF example that we saw, would be an unequal distribution of electron density in a polar covalent bond. So an unequal distribution of electron density in a covalent bond. So we're still sharing the electrons, we're just not sharing equally. In general, the farther apart 2 atoms are on the periodic table, the more likely it's a polar covalent bond. Common examples that we'll see, right? We already saw HF, but HCl is also a polar covalent bond. Things like a hydrogen-nitrogen bond, or a hydrogen-oxygen bond, or a carbon-oxygen bond. All of those would be polar covalent bonds because in this case, fluorine is more electronegative than hydrogen. Chlorine is more electronegative than hydrogen. Nitrogen is more electronegative. Oxygen is more electronegative. And oxygen is more electronegative than carbon as well. So in all of these cases, I have a covalent bond. I'm sharing electron density between those 2 atoms. I'm just not sharing it equally. It's closer, the electron density is closer to the more electronegative atom in that molecule. And so in general, if I gave you the electronegativity of the atoms, right, something where the difference in electronegativity is 0 to less than 0.5, that's essentially nonpolar. We've got almost equal distribution of the electron density. The polar covalent bonds, we're going to have a difference in electronegativity between the two atoms that are bonded together from 0.5 to less than 1.9. So HF is right at the boundary of what can be a polar covalent bond. And then beyond that, if I have a difference of larger than 1.9 between the atoms that I'm putting together, I'm no longer a covalent bond. I can no longer share those electrons. I'm going to have a transfer of electrons, and that would be an ionic bond. So anything greater than 1.9 would be ionic bond. We're going to generally see that when we see our metals reacting with our nonmetals. These two are going to apply to when we're talking about nonmetals reacting with nonmetals. We're forming covalent bonds, and we're either sharing that electron density equally or almost equally in a nonpolar bond, or we have an unequal distribution of electron density in a polar covalent bond. And so those differences in electronegativity, those are what establish bond dipole, or essentially partial charges that are assigned to each atom in a covalent bond. Partial charges assigned to atoms in a covalent bond based on differences in electronegativity and based on their density of electrons. So based on differences in electronegativity and as a result, differences in their electron density. And that's what I tried to show earlier when I was talking about HF, and I was representing it as a vector, indicating that on the HF, fluorine is pulling electron density closer toward itself, and so our electron density would reside closer to fluorine, creating a partial negative charge on the fluorine. And because more of that electron density is pulled away from the hydrogen, I'm going to have a partial positive charge on that hydrogen. That's what's going to establish my bond dipole, the separation of a partial positive and a partial negative charge in that molecule. And we can see that here with these dipole moments and also looking at the differences in electronegativity. So as I go from fluorine to chlorine down to iodine, I'm going to get a decrease in electronegativity. So fluorine is the most electronegative, so I'm going to have the largest imbalance of electron density. I see that in this electron density map, right? Most of the electron density is on the side of the fluorine. As I go to chlorine, chlorine's a little bit less electronegative, so my difference is a little bit smaller. Bromine's even less electronegative. I've got a smaller difference in electronegativity. And then iodine is even less electronegative, and we see closer to an equal distribution of electron density. So that vector is going to get smaller and smaller and smaller until essentially hydrogen iodide is a nonpolar covalent bond. We've got approximately equal distribution of electron density. And that's represented as well in that dipole moment. The dipole moment gets smaller as I go down that row because my difference in electronegativity is getting smaller. This is important in determining the properties of these molecules. It's going to determine their intermolecular forces and things like the boiling point and viscosity of these molecules when they are in solution. So the important things from today, we should be able to differentiate between ionic bonding and covalent bonding. You should be able to represent an ionic bond through Lewis structures and think about when a metal and a nonmetal react in an ionic bond, how they're going to change and exchange electrons between the two to form an ionic compound, as well as thinking about molecular compounds with respect to the Lewis dot diagrams and representing that each of those elements in a molecular compound wants to obtain a full octet of electrons through sharing electrons. Obviously, with some of the exceptions, like hydrogen, for example, that will never have more than 2 electrons in its outer shell. So in the next class on Wednesday, we're going to start drawing more of these Lewis structures for covalent molecules. So Wednesday is going to be a very important class where we're going to practice a few more rules to drawing Lewis structures for covalent molecules.